Work and testing on this device will involve handling high voltage that can shock, injure, or possibly kill you if handled improperly. Please take all the necessary precautions when working on this or any other device that may contain high voltages. Hello and welcome to part 4 of the Sencore ES-102 capacitor substitution box restoral. I have gotten to the point where I am ready to do final assembly and hopefully testing on this. And what I did is I took the one switch that we're going to use. I used a assortment of things on it. I ended up taking some dielectric grease and using that for a lubricant to lubricate the mechanical stops, spring stops with the ball bearings. It's got two ball bearings here with mechanical springs to stop here and there. I'm doing some preemptive cleaning and lubrication just to make sure this thing doesn't turn into a problem down the line. I took there's two screws that hold the assembly together. I tightened these a little better and I put a little bit of green thread locker on it. It's a penetrating locker. You don't have to take things apart to use it. It'll actually seep into the threads a bit, harden up, and then lock. And then I also put some heat shrink on the hardware because these two will be bumping into the two larger capacitor array bodies. And then I took a little bit of everybody's favorite switch cleaner there, and I just went through and took a little swab and cleaned up most of the contacts that I could a little better and put some cleaner lubrication on there. It should leave a little residue of lubrication that hopefully over time it'll behave and it won't be an issue. So that's where I've got with this so far. This switch had a larger shaft on it. I ended up in a different hardware configuration. there was a tab sticking up when I first got it. It was made to protrude through a hole in an enclosure face to keep the assembly from rotating. But the problem is I don't plan to modify that with a hole, so I ended up bending it over and then had to find a large enough hardware washer. This was a 3/8 internal star lock washer that will fit the metal on the switch very well and goes onto the shaft easily. And then we can get to the point where we can start installing this guy. I ended up checking this thing for alignment before. I indexed it and put a small black mark on the inside of the cover and one on the switch as well. I don't know if you can see it, but it's not that big of a deal. And then my hardware is going to end up a little bit out of line from side to side, but it doesn't matter that much. It'll just give a little more clearance on those two larger capacitors. And then the depth on this is a little less than what I thought, but everything should go together fine here. So then all I really have to do is put a flat washer and a hardware washer. This is hardware that came with this new switch. I had since the shaft diameter is a little bit larger. The D portion of this lines up. I've got it on the lowest setting and it lines up with the number 4, so we are going to tighten it up as soon as I can find out what happened to my little pair of channel lock pliers. Slip joint. Well, these are channel locks. See how the knob lines up on the switching there. I have this so it'll about, it's a little loose. I can tighten it up. So I can index this properly to the positions. It's got a little play in the knob. I don't have the spring exact, but it looks like it's oh, we're out of focus there. Here we go. It looks like going around the horn that it lines up fairly well with the marked indexes on the cover. So that's the last of its installation positioning. I'll just put a small dab of that on the threads, and it hopefully should hold it in place for the future. I tightened it down so much that I felt that star washer compress a little bit when I did it, so it should be very secure. I'm not going to worry about putting the switch knob on here right now because it will be resting on its head for a while. And then what I did also is I went through and I indexed all these switch position values on the leads to cut confusion down, because I really only want to do this once. We're probably going to orient this so the box is in this position. I have all the capacitors labeled for values and the voltage, and also the fact that the black is the common negative on here. So as far as the values, the small red one is going to be the easiest because it's all the smallest values, and then the red taped one, and then after that the larger ones have values in descending order, but they're not sequential as far as the total value of the two larger ones. So I'm going to have to pay attention making the connections on those, and I'm going to leave the black leads for last out of all the connections. Those are going to be the commons, and they're basically going to be tied directly to the common on the common negative. I believe it's going to go, I drew up a schematic for this, so I can go over it, because it's going to get complicated once I got to put the switch back together still, and then the leads. It'll get a little complicated, but I drew up what I'd like to accomplish as far as the test positions for that switch. I'll just have to get a hand-drawn schematic for it. I don't know of a software for doing layouts of printed circuit boards that has a symbol for a multiple position rotary switch. So we're just going to go with a hand-drawn schematic. Maybe someday in the future I'll find one and create a little better looking thing. So I'm going to get the soldering iron to warm up, and we will be back and start to make our connections. Okay, I fibbed about showing you the soldering. You've probably tired of seeing soldering from my earlier parts on this video, so we'll leave that out for now. I've got all my positive value leads soldered on the rotary switch. I have the common center not terminated. I'm going to put my meter onto that guy, and I have all of my negatives connected in parallel to the other side of the meter, and we'll go over and test things. Pardon my switch for being upside down right now, but it's the way it's going to be for right now. I've got it on the 4 microfarad position, and it reads 4.46 nanos. The 10 switches over to 9.7. 20 is connected to my 22. 40 comes up as a 37. 60 is a 61. 80 is 80. 100 is 99.65. 150 is a 151. 225 comes up in a 214. And my 350 is a 351. So my connections on a rotary switch are all good. Now I have to complete the connections for the rest of the box, and I will go over the schematic I drew up beforehand to show you the functioning I wanted to do with this surge protector switch. It's an odd switch. It's a 3-position switch, but I'll show you the configuration on that as we go further into this. So, be back in a bit. Here is a view of the innards of our switch for reassembly. Like I said, this is a 4-contact switch with only one piece of electrical contact material in the moving portion of the switch. I'll zoom in a little bit here. And what's going to happen is, depending on what position it's in, it will just make contact with 2 pins at once. And it's got a little raised part to be a detent. So as you move it along, it's going to contact the end to one of the center, towards the one side, the 2 centers, or the other end and the other center. So we have to keep that in mind when we are going to wire the device back up to function. And I could not find a original schematic for this guy anywhere, so I'm going to, and the fact that I did change this switch to a different type. Like I said, the old one contacted 3 of the positive capacitor leads at once, whereas this one only contacts 1. So there are some differences in things, and that's why it's not a faithful restoration of, it's a modification along with restoring it. So I'll go over the schematic with you next. And finally, I have arrived with the working versions of the functional box that I'd like to use for my final version. I'm going to go over what I did and some of the things and how I wired it. The main thing was I added banana jacks to connect to the top of the box from the positive and negative test leads. They're permanently connected, and what that does is it gives me the opportunity to hook up a meter on that part of the box and monitor either the voltage or the capacitance or resistance in a circuit while I'm working on it without having to grab another meter or use more test leads than I need to do things. It also allows me to check the voltage on a capacitor that I am trying to discharge in a circuit or another piece of equipment in order to remove it safely or to work in that area. So that's the first item I did. And then the slide switches on the box itself. Kind of get that into view here. This has a slide switch that has 3 positions on it. It is spring loaded to mostly stay activated on to the right. Has a center position and a far right position, and between the two it has contacts. There's 4 contacts in there, but there's only a contact material that connects 2 of the poles of the switch at a time. So out of the 3 positions, the first position, that it's the spring-loaded one, that's going to be the normal position. It's going to be spring-loaded to the left, and it connects the selected capacitor value on the unit to the test lead. So if I need to add a value into something I'm working on, all I have to do is select the value on the rotary knob and connect the leads. If I'd like to use it for discharging functions, I would momentarily slide the slider switch over to the center position and hold it, and that would connect the internal 500 ohm 10 watt resistor to the test leads to use the discharge capacitors in the equipment under test. So like I said, if I needed to work near a capacitor that was recently charged up to 400 volts, wanted to make sure it was safe, I could connect a DVM or other type of voltmeter to the box and then monitor the discharge voltage on it as I discharged it to make sure goes down to a safe voltage to work on. And then the third position is the position manually that has to be manually slid over to the far right, and that would allow me to discharge a capacitor inside the box that's been charged up during use. Let's say I used a 350 microfarad capacitor, connected it to a piece of equipment for a while, and it stored a charge, and I'd have no good safe way of discharging it besides shorting the leads out, and that's not the best thing to do to capacitors for longevity. It puts a lot of stress on them, and not to mention the contacts inside the box. But if you discharge things through a 10 ohm resistor or the 500 ohm resistor, it does minimize the impact of wear on the capacitor, and it does take a little time to do that depending on the voltage of the capacitance, the voltage and the capacitance on the item that you're discharging. But we'll experiment and go over that in a little bit. I have a web page calculator that I found on Digikey that's fairly interesting. I'll go over that with you in a minute. Here's a web page that I found on Digikey in their tools and conversion calculators sections, called the Capacitor Safety Discharge Calculator. What this web page does is it lets you put in a known capacitance value with a charge voltage, a safety threshold voltage, which would be the voltage that you'd consider safe to work with that capacitor on at the discharge point, and it'll solve it for the time. And also you have to enter a resistance value. So in this case we have a known resistance value of 500 ohms, which is automatically sets for ohms. Capacitance value, we're going to go 350 microfarad. The default is microfarad. Initial charge voltage, we can go up to 120 volts because I do have a source for that. Now we don't know how long it's going to take to get that capacitor down to, let's say, 10 volts. And according to this calculator page, if we solve it for time, it says the safe voltage is achieved in 1/2 second. Initial power across the resistor is 28 watts, but that is dissipated very quickly. So it's not, you can use a resistor with a lower wattage than what the calculator comes out with for the initial power. Time constant is 1/8 of a second, and the energy discharged to 0 volts equals 2.52 joules. So I'm going to use this page a few times in this video, once as a reference for the 350 volt capacitor as I charge and discharge it. And then again, I have a larger capacitor, got a 3000 microfarad that I can charge up to its rated capacity of 100 volts, I think, and then discharge that one as well. So we'll be getting into that later, but in the meantime, let's go over the schematic of how I connected things inside the unit. And here is my final schematic for what I did to the original unit and wiring. Like I said, I had to replace the switch with a non-stock switch because I couldn't source the switch that connected 3 capacitors at once. And then I also chose to add more functionality into the box. And then the third item was I couldn't find a stock schematic and owner's manual, user manual for this thing to save my life anyhow, so I ended up making some stuff up as I go along here. One of the most important tools in designing this thing, I had to use that quite a bit to make a few changes in order to finally get the thing to work how I wanted to. That seemed to make sense to me, so we'll go over some things again. I hardwired 2 banana jacks on the back of the unit. I'll show those to you quick. Positive and negative, and those I'll give you an internal view after I go over the schematic. But so those are hardwired through to the the black test lead goes around to the bus here, and that goes to the negative connection. Positive test lead I have wired to what would be considered one spare contact at the end of the switch selections past the 350 microfarad capacitor. That gives me the ability to connect this in one instance where it might be useful. And other than that, the switch, when it's wired up through the first two positions, like I said, this is a 4-contact switch, but it only has 2 contacts that can be connected at once. And this slider would be spring-loaded to stay in positions 1 and 2 normally, and it has to be manually indexed over to 2 and 3, which is the position to connect the 500 ohm resistor to the test leads. What happens is if you move the slider switch over and hold it for a few moments, it will take the positive test lead, connect it through this contact through the 500 ohm resistor to the negative, up, around, and over out to the black test lead. So that gives me the ability to discharge the capacitor in a device under test, or the free-floating capacitor, without having to connect another load or short it out. This resistor I've got mounted on a little piece of aluminum heatsink inside the box. We'll see how things perform after a bit. And then if I hold the switch over manually to the far right, it will take the selected common position capacitor, whichever value it was, probably the last one I wanted to use, because that would be the one I'd want to discharge, that might be holding voltage. It would connect that to the 500 ohm resistor, and then directly to the negative side of the commutative negative for all the capacitors. So that will discharge the capacitor that's inside of the unit without having to hook up another external load to do so. So it'll keep me from excuse me, from damaging myself or something else I might connect it to. So that's the schematic part of it, and then I'll go over the internals. What I did was I ended up wiring this up with some what would be considered a maintenance slack loop to be able to get the cover in and off. It's got some excess wire on it, but it does have enough so you can pull the cover off and things not being too tight. So here's the connections for all the negatives. And I've got a 500 ohm resistor. I've got to secure this a little better with some glue or something, but it's on a little aluminum tab. And here's the capacitors with their marked values on everything, the color codes, ratings. And then here's the switch wiring for the 4-position switch. It shows the loop between 1 and 4 that was on the schematic. And then everything also just wiring things up to positions on the switch. I ended up marking the values of what I was going to connect things, so it kind of kept the confusion down a little bit, and just a little soldering and reworking. And I reused the original test leads on the unit, test lead, test clips. They were still in pretty good shape. I just resoldered connections on them, and put some half-hitch knots on the backside of the cable to hold things in place, and that's about it. And all the other little things I did is I went out of the way to install some. Didn't do the best job, and I have to touch up the paint, but I went out of the way to install some machine thread riv nuts on the box to hold the cover on. I never like sheet metal screws going into plain metal and things if I can avoid it. So that's about it. It all crams back into place, and I'll put some rubber feet on it. And then going forward from here, we can go over the functions on the box itself, or how it performs. So I've got my capacitance meter handy here. Right now it's hooked up to the leads coming off the test spots. It's hooked up to the capacity, and all that really does is in one function it connects in the far right function it connects the banana jacks to the test leads, And every other function going down the line will rotate through all the connections itself. This one's comes up as a 352 for a 350, 214 for a 225, 150 for a 151, 99.9 for 100, 80.2324 for 80, 61.5 for 60, 36.8 for a 40, 21.9 for a 20, 9.8 for a 10, and 4470 nanos for a 4, so that's 4.46 nanos. So the capacitance part works well, and their next test would be to check its functionality for discharging capacitors. Got a meter that I can set for, I need to set it for 4K. So right now it is just connected to a short pair of banana to bananas, so I can connect to the box with it in a little bit. But if I'd like to discharge a capacitor that this might have been connected to, but this box is being used to bypass, all I would have to do is slide the switch to the middle position, hold it there for 4 to 5 seconds, and we've got 493.493 kilo ohms, so about 500 ohms on it. And then things, as far as the other functionality, I have to get a voltage source and another capacitor involved. I will do that in just a little bit. And I am back. I found the voltage source and have it connected. Off camera is a Hewlett-Packard E3612A 0 to 120 volt power supply. It's not the star of this show, but will be featured on an upcoming video because I have to recap it and go over a flaw that apparently was designed in the original unit, and this caused problems for a couple other units. There's a couple other YouTube channel owners that had to do some repairs from a capacitor, same capacitor that kind of blew up and puked all over the board, and luckily mine hasn't done that. But I think I found out why it's actually doing that, and I'm going to apply the fix to it before my capacitor pukes. So in the meantime here, I've got the 4 microfarad capacitor selected. These are all 450 volt rated, same as the originals. So I can safely take this up to 120 volts. And I have to switch. This box has 2 ratings. I got to switch it in the high gear lower current to go to the higher voltage. That's going to use this to demonstrate the capability of this unit to discharge capacitors. So now we're at 100 and got 120 indicated on the meter, 121.8 on this one. The voltage supply has to go through calibration as well. But in the meantime, this capacitor right now, if I disconnect it, and I'm going to try to use the best safety practices possible, which means only trying to do things with one hand, I'm going to disconnect it at the meter itself. See, we still have a capacitor slowly discharging, and what I'm going to do is hold the switch all the way over to the far right for a little bit and release it, and if you see that capacitor is building a charge back up, which those capacitors will do that, but they won't do it back to their full voltage. So that's at the 4 microfarad value. So I'm going to go nuts and go all the way over to the 100 to the 350 microfarad value. I'm going to turn my voltmeter down first. Hook my connection back up. Trying to apply the practice that electricians should use a lot of, keeping one hand in your pocket whenever you're dealing with hazardous voltages. It's the best way to not get shocked. So we have a 350 microfarad capacitor connected, and I'm going to raise the voltage on this one. Okay, we're up at 120 indicated on the unit, 120 on our ohm meter, so I am going to disconnect my positive from my power supply. And if you see, that's still holding quite a charge for a while on the test leads. But what I'm going to do is hold it over to the discharge position for about 5 seconds. Release it, and we are down to 0.2, 0.3 volts. Basically a safe voltage to work with. It might build up a charge, but it won't build up a charge to the point where it's going to damage you and probably not the equipment that you're working on. So that's a worthwhile function to have in this meter. It was designed into there to begin with, but you couldn't monitor what was going on as far as discharging the capacitor itself. So if you bear with me here, I do have one more. Here we go. I've got an old Dynaco amplifier, ST120 amplifier, power supply capacitor, 3300 and 100 working volts, 150 surge. I measured this out at about 3400 microfarads with ESR of somewhere 0.8 to 0.95, depending on which meter I used. The positive lead is facing me, so I am going to hook up the positive lead of my discharge box. The negative lead of the discharge box. I'm going to switch this over to just capacity, but what that does is it doesn't connect any of the capacitors inside the unit. It just connects, makes sure that the positive test lead is connected to the positive test lead through the switch, which it is bridged to anyways, but this way it isolates any of the internal capacitors from the unit. So I'll hook up the negative to the capacitor. Let me turn the voltage down on the power supply again. And my last connection will be positive to the capacitor, positive. So we have 2.1 on the unit. We're showing 2.1 on the voltmeter, so let's go up in scale. I have the supply set for only a 9 or 10 milliamp output, so when it does hit its charge, it should come off of constant current. Okay, hit the 27.6. It hit switched off. I might give it 20 milliamps because it's there we go. So to make sure this capacitor isn't shorting out on me as they go here. If you notice, just charging it with 20 milliamps takes a little while. Could be reforming a bit to its satellite. These capacitors are from the late 1960s to early 1970s, depending on the vintage. Okay, I'm going to give it a little more current, 30 milliamps. The voltage on the power supply is actually climbing, so I might have to turn it down once I get close to 90 or so, because I don't know what the set point is, since it doesn't tell me what the actual set point is. I think I'm getting close to the... Here we go. Okay, my set point for the voltage is 85.3. We'll go up a little higher. Okay, we've got it up to 100 volt charge. And it has got an 11 milliamp charge current going into it. It is still taking a little bit, but it's dropping, so it's reforming. I can't really say it's heating up to the touch at all, so it wasn't in terrible shape to begin with. Like I said, it tested well. But it has a few joules of energy in it, so we are going to leave it at this, and I'm going to disconnect the positive lead from the meter, or I mean from the power supply, and it is discharging. Turn the power supply off so it's on its own. So now what we are going to do is, all I have to do to discharge this is to slide my slide switcher to the middle position. So we're going to do that and watch the voltage drop. And the capacitor should be safe to work with now. So out of curiosity, I'm going to go back to the calculator and see how much time it calculates a 3300, 3400 microfarad capacitor at 100 volts down to a voltage of 2 volts, because it was about 7 seconds or so. So I'll go back on the website and calculate that. Okay, so back on the website, we're going to change a few values. On the calculator, we're going to change this to a 3400 microfarad. Initial charge voltage of 120. Safety threshold, we're going to go about 2 volts with a 500 ohm resistor, and sort for time. Solve for time, and the time says safe voltage achieved by 6.96038 seconds, which is probably very damn close to what it took. Again, the wattage across the resistor was only 28 watts initially, time constant 1.7, and the energy discharge to 0 volts would be 24.48 joules of energy, so quite a bit more than the 350 microfarad. So that gives you a good idea of the functionality of discharging a resistor, what it takes to do, and in this case it can be monitored while I'm working on equipment when I'm using this electro sub box. So it's seems to be something that it's really desirable to use the way I have it configured now, and I'm going to go forward and hopefully be able to use it in applications for doing troubleshooting and repair. And so there we have the completed unit, tested and ready to go. One thing I would like to go over is I ran into one strange issue with these switches, being that they are sourced from a Chinese supplier. The manufacturing on these leaves a little bit to be desired, and I found out that after putting it into use for a little bit, I had an issue where there is a metal ring that holds the shaft in place here. This ring is almost as soft as solder. It is like some of the softest steel, metal, whatever you want to call it, I've seen. It ended up popping off the shaft, moving up a little bit, and I ended up having to push the shaft back up, crimping it into place. So what I was able to do, hopefully a little bit, was to put these two ends actually got to the point where they lined up together where I crimped it in better, and then I ended up putting some solder in there, hopefully to hold it for a while. If it becomes an issue in the future, I'm going to have to remove this and find a suitable snap ring to replace that with. But there is a small groove that it goes into on the shaft that holds everything into place, and I noticed that the spring tension on the mechanism on the detents was getting awful wobbly. This shaft kind of floats in space here. There's no real bushing or anything back here to define manufacturing quality, so it just turned into something that I had to apply a on-the-fly fix to. If it becomes a problem later, like I said, I'll have to apply a little more attention to it, some different parts. But there is enough space to put a snap ring behind it on the switch. They do give you knobs that slide on the top, and the snap ring shouldn't interfere with the knob being seated fully. If it does, you can always hold the knob off a little bit, stand it off a little bit as you tighten it. The one nice thing about this is at least it does have a flat machine on the shaft. Helps with holding the set screw a little better, and I did file mine a little flatter because that one doesn't have a real flat surface on it. Filed it flat a little bit, and then I used some of that green Loctite on it. They found that green Loctite is quite tenacious. It's just about as bad as the red stuff. I might have to get a bottle of blue stuff, because the blue will kind of hold things in tension, but they won't really lock them in as firmly as the green stuff. It's pretty, like I said, it's pretty tenacious. So that's about it. I'm just going to apply some rubber feet to it, like I said, and put screws on the side of it and fix that resistor on that piece of aluminum angle a little better. I was using for a heatsink, but other than that, it should be a working version of, and I thank you for viewing this video and sticking it out with me, and I hope that you gained some knowledge or something as far as the original goings-on inside of one of these, and or being able to modify it to something that might be more usable for you. So my schematic and configuration is by no means the last word in what to do with something like this. Everybody has their own levels of creativity and what they might want to design as far as functionality, but you've got possibilities with it once you open it up. You just have to get your hands on one and start playing with it. So I thank you very much for watching the video again, and I hope to see you again. I'm going to have some upcoming test equipment recaps and repairs, and even design on a power supply board, a linear power supply board for a FY6600 arbitrary wave generator. I'm going to take a stab at that. So hope to see you again soon, and thank you for viewing. This content is available on YouTube and Odyssey.com. If you enjoyed this, please like and subscribe. Hope you return soon.